Okay, we're in Chapter 7, Section 1, Problem number 5. A random sample and size of 144, so we've got n equals 144, is drawn from a population whose distribution, mean, and standard deviation are all unknown. Key there. The summary statistics are x bar equals 58.2 and this equals 2.6. So our mean is 58.2 on our sample and our sample standard deviation is 2.6. All right, so let's look at A. In A, we're to construct an 80% confidence interval. So 80% on our confidence interval is our 100 times 1 minus alpha percent confidence interval. So our alpha is going to be 20% or 0.20. Okay. For the population mean mu. All right, so our n is greater than 30, so we know our sample size is large, so we can use our large sample size formulas. So for our confidence interval, we use the formula x bar plus or minus z of alpha over 2. Now this, depending if we know or don't know our standard deviation of our actual population, if we know it, we use it. If we don't know it, we're going to use our sample standard deviation divided by square root of n. And let's see, so we're going to need our z of alpha over 2. So alpha was 0.20, alpha over 2 would be 0.10. And to get this then, we're going to have to look for our z value. We'll have to look inside the table to find the percentage of 0.10 and then read to the outside of the table to get our z value. So in doing that, looking in the table and finding that and then pulling that out, our z value for the percentage of 0.10 is going to be 1.282. So we can substitute in now. We think we got all our values. So we have 58.2, our mean, plus or minus our z value, 1.282, times our sample standard deviation, divided by the square root of our sample size, which will give us 58.2 plus or minus 0.28. So we could say that's going to be, let's see, 57.92 comma 58.56. We can do that. Okay, so for B then, we're going to be doing, okay, a 90% confidence interval for the population mean mu. So we're doing the same thing, but a different confidence interval. So our confidence interval is going to, we want a 90% confidence interval. This is our 100 times 1 minus alpha percent. Our alpha is going to be 10% or 0.10. So we're going to have a z of alpha over 2, so that's 0.05. And so we look in our table for where the table is 0.05 of a percentage, and then come to the outside to get our z value, and that's going to be our 1.645. So again, back into that same formula, because all we've changed here is our alpha level. So we have our same 58.2, but this time it's going to be plus or minus 1.645. And our same s and square root of n. So we're going to have 58.2 plus or minus. Okay, in this case it's going to be 0.36, which will give us a range of 57.84 to 58.56, which reminds me that I wrote it up above there, so I was going off some. Imagine that, made a mistake on one. So happens to all of us, obviously. Okay, so if I add 0.28 to 58.2, that's 0.48. Had that wrong there. All right, so I've got those correct now. Let's go to C. Comment on why one interval is longer than the other. So in our 90% confidence interval, it was plus or minus 0.36. So that's a wider interval than our 80% confidence interval, which is only plus or minus 0.28. So why is that? So if we want to be 80% confidence, well, we're 20%, we can have misses, so the tails will be bigger. So if the tails are bigger, then what's left inside is smaller, so we have a smaller window. If we want to make sure we capture more of our whole of making sure that we've got a high percentage of catching the mean, then our confidence interval has to be larger. So that's why it's 0.36. We had to catch so that's less tail out there. So a bigger space means it's going to be a bigger interval. So the more confidence we want, the bigger that interval has to be. The more accurate the smaller we want that interval, the less confident we are that it's going to contain the population mean. Okay, check.